I stand between you and the cocktail hour, I understand, at 4 o'clock. It's a dubious position to be in, but it's always good to fill the room because you guys come in, you got to do something before the cocktail hour. My name is Arya Barirani. I work for Infoblox. I run product marketing for them, and we're based out of Santa Clara. We're predominantly focused in DNS technology, which is why I'm here to talk to you guys about DNS and the role that it plays in the network. And the way we packaged up the brief is that DNS can either help you in your pursuit for a more secure environment, or it can become an Achilles heel. And a lot of folks aren't very familiar with DNS, especially the folks that live in the world of security. Networking teams generally responsible for it. Sometimes the server teams and the operating system teams are responsible for it. It's one of those unique functions inside of the network that is super critical, but it also kind of floats around different groups. So sometimes, one group thinks that someone else is responsible for it. So what we're trying to do is create greater awareness around this, and it's a great opportunity for us to have a dialogue. I'm going to talk for about 30 minutes, and if you have a question that's a really pressing one, raise your hand and I'll be glad to address it. I'm going to be joined hopefully a little bit later as the guys set up. We have an exhibit back there, but Fernando Gaudi, our account exec for state and local government, and Ryan Edel, our systems engineer, will probably join in the room, and I might refer to them if you guys go really deep on me. I'll have to invoke Ryan because he's our real technical depth. So let's get into the agenda. So first, I'm going to give you guys a primer on the domain name system, DNS, and some of you guys may be familiar if you're working with DNS today. Bear with me and indulge me as I give you guys a remedial high-level course, but if you're not, I think this will give you a good grounding in what it is at a very high level. And then we're going to talk about the threat landscape and how it impacts DNS. And we're going to get into a couple common attack vectors so you understand how the bad guys or our adversary, there's Ryan. Ryan Edel, everybody, welcome. How our adversaries are using DNS as a vehicle to exfiltrate data, to bring down systems. And then we're going to talk some best practices on how to protect yourself. So that's the agenda for today, and we'll try to keep it light and lively. I know this is a late afternoon. We'd love to have a discussion. If you have an experience that you want to share with the rest of the room, I think this is kind of the spirit of what these events are all about. It's education, it's best practices sharing, so don't let me be the only one. If you have something you want to add during the QA session, please do. Okay. So what is the domain name system? Well, it's the address book of the internet, and it was designed in 1983. After TCP/IP was basically created in the late 70s by ARPANET, these guys came along in the early 80s as a way to make it easier for organizations to basically connect to each other's servers and share information. So Paul Mukapetris from UC Irvine and a number of folks from UC Berkeley got together and they created the domain name system. And the domain name system, the first instantiation of it, which ran on Unix, was a Berkeley distribution. And you may have heard of Bind. That comes from Berkeley. So it was a bunch of universities that got together and they created the standard which allowed people to be able to connect servers together in a way that would allow for names that we can understand, like google.com, and translate those to IP addresses that computers would understand. And by using the domain name system, you could use these domains and they could have multiple servers underneath them. You wouldn't have collisions, and basically connects everything and anything on the internet to one another. So realistically, without the domain name system today, the internet and network communications would essentially come to a halt. If you go to any organization today and say, let's turn off DNS for 24 hours, they just couldn't do it, right? So critical infrastructure, in fact, IETF, the group that kind of sets the internet standards back in the late 90s, finally succumbed to creating a standard around this and calling it critical internet infrastructure officially. Yet it's something that is kind of misunderstood or little understood in terms of the role that it plays and the criticality of it. So how does it work? So you got these endpoints over here that are trying to get access to let's say a resource like google.com, and that's actually the IP address for google.com. So the endpoint says, all right, you're in your browser, you type in google.com, I need directions to that server. So the request goes up as a query to your ISP DNS server, and your ISP DNS server may or may not have that information. I'm kind of for illustration purposes saying that the ISP DNS server in this case does not have the information. So it says, okay, I don't know where that is. I'm going to ask another server. That's called recursion. So now it's going to go up to another server that's authoritative for that domain, and is going to say, all right, I don't have it. I'm going to go ask somebody else. So this can continue to go up several servers to other recursive servers, and eventually to possibly even a root server that is authoritative for that domain. And the root server says, I know where google.com, I know the IP address of google.com, I'm going to give that to you. So that's in my cache, and it maps to that address. That information is passed on. The server says, great, I'll put that in my cache in case someone else asks for it, and I'll hold on to it for a while. And this is where the notion of caching comes in. You take these addresses, and these DNS servers put those in their cache. And one of the problems that you run into is that sometimes these caches get populated with information that might be outdated, or it may be actually a domain destination that's malicious. So when a problem happens in DNS, it doesn't unwind itself automatically, because these caches have to time out and clear out. So when you see cache poisoning, for example, where malicious domain destinations are inserted by bad guys in here, it takes time for them to kind of unwind through the system. So okay, so it puts it in its cache and then provides the IP address, and it allows the endpoint to be able to get home. Now in this process, a lot of things happen. And this happens instantaneously in the system, and it also allows for a lot of kind of crazy bad things to also be inserted into the process. We'll talk about some of those. The behavior of these servers, how they take data, how they move data around, all of these are creating potential vulnerabilities that bad guys can exploit. And we'll talk about that a little bit. So high level, that's how it works. For our adversary, DNS is a great target. Why? Because it's kind of the foundation of internet communications by most businesses and governments. It's fairly easy to exploit. We talked about how it was designed in 1983, and you know, it's a stateless protocol. The servers are generally very trusting of one another. If I get a request, I only do one thing. The protocol just responds. So if you ask for me where google.com is, that domain, I give you an IP address, and I don't think about it too much. I just kind of respond, and I don't think about what came before. So stateless in the sense that I don't have any real memory of the previous query, and it may have been related or may have not been related. But some of these things are becoming kind of an Achilles heel in the world of DNS, because it's generally a simple and trusting protocol and designed to do one thing, which is I ask it for something and it gives me something back. So fairly easy to exploit. And traditional protection is generally ineffective, because a lot of the perimeter security tools that we're using, the malware tools that we're using, all of these great technologies that you may have even been talking about, while those are very, very important in different parts of the network, they're not really focused on DNS traffic, or very seldom focused on DNS traffic. Your traditional firewalls are set up to pass port 53, kind of uninspected. Inbound and outbound port 53, generally, you know, in most of the best practices documentation that you'll find with your firewall providers, generally leave it open. Now, people are beginning to learn that we need to inspect that traffic and be careful about it, but most firewalls don't understand the protocol and can't tease it apart to be able to see if there's some malicious activity happening. And our adversaries are beginning to focus on it. So in the last couple of years, we've seen a pretty significant rise in attacks, specifically external attacks to DNS. So one of the ways that they try to bring down DNS is through these DDoS attacks or volumetric attacks, just hammering your DNS server so that it can't now serve up the address of your website, puts you out of business. We're seeing a doubling of the attacks around DNS. And one of the things that we'll talk about is that the query response mechanism can be asymmetric. In other words, I might send a 10 kilobyte query and get a 100x response back. So there's an amplification that can happen depending on how the DNS server is configured, which may allow bad guys to be able to use that amplification as a way to attack others. So we'll talk about reflection and amplification attacks. These are the kinds of things that can happen. There are, to our last count, about 33 million open recursive DNS servers out there. An open recursive DNS server is just a DNS server that's configured to respond to any query without authenticating the requester's IP address. So what happens is that if you're an open recursive DNS server, you can actually be spoofed. Someone can actually ask you for a query and force the response to someone else. And this is what a reflection attack really is when the bad guy spoofs his IP address so that the DNS server responds to the target destination. And if you ask for enough of those, you can potentially bring down, you can actually DDoS your target. We'll break that down in the vectors. And with, on the average, 2 million DNS queries being served up by most organizations every day, it's hard to detect and anomalous patterns. So there's a lot happening in the network. It's hard to detect. So again, kind of a little bit of repeat. Easy to spoof, asymmetric amplification. And here are the top 10 countries where a lot of the DNS DDoS attacks came from last year. Probably not a huge surprise, but this is where they come from. If you talk to some of the customers that we talk to, they're experiencing these every day. We have some customers that are in critical financial infrastructure, trading room floors, stock exchanges, reserve banks. They're experiencing these attacks on a daily basis. In fact, I asked one of them, I said, have you ever experienced a DNS DDoS attack? And he's like, you should reverse that question. You should ask me, what day am I not being attacked? Because I'm defending all the time. There's no shortage of bad guys around the world that are just trying to constantly test and break this stuff down. And it's happening every day. And I'm going to kind of skip this one a little bit. It talks about the industries that are targeted, financial services, very high. And we believe that government sector, also federal government. You guys can tell me what your experiences are regarding state and local, but it can be pretty expensive if your DNS infrastructure comes down because you're pretty much out of business. So let's talk about a few common attack vectors. The way we look at the world is that there are three primary challenges that we need to help with in terms of securing DNS. One is securing the DNS platform itself. That's the server that might be sitting in your data center that is serving up and responses to those queries every day. The second is defending against DNS attacks that are external, like denial of service, volumetric type of attacks that are designed to bring down your DNS server through different kinds of nefarious attacks. And the third area is preventing malware from using DNS. There's a couple use cases where we see customers are actually using malware exfiltrating data using DNS. It's called DNS tunneling. You can actually put data payload on the back of a DNS query on an outbound DNS response, and the DNS server won't be any wiser for it. They're small packets, but we've seen instances where a DNS port 53 is used as a tunnel to exfiltrate data or bring in malware payload. We also know that malware, which is just an application sitting on an endpoint or on a server, generally use DNS, the domain name system, to get to their botnet controllers. They generally don't hard code IP addresses in malware payloads, right? Because if they did, we'd find those servers and we'd be able to shut them down. So they have to use DNS with domain generating algorithms to be able to call home. So DNS is often used as a vehicle like any other application to get to the internet, and malware is using it. And this is where the Achilles heel could become an asset, which is if I am seeing where every endpoint and every application, which domains they're trying to access. If I had some knowledge about those malicious domains, maybe I would be able to stop those queries from happening. Or if I wanted to establish some policies that said, there really shouldn't be any reason why any endpoint or any application in my system should try to be accessing Moldova domains, right? Maybe I can use my DNS server as a vehicle to stop that communication. And the elegance and the beauty of that is that DNS is a multi-protocol type of service, right? So it doesn't matter what the communication mechanism is. It could be HTTP, it could be IRC, which is chat, SMTP, which is email, it could be FTP communications. It doesn't matter the networking protocol that you're using for the communication. To resolve to your destination, you still need to use DNS. So DNS can become a multi-protocol choke for potential malware communications across a whole bunch of different services. And this is where things get interesting, because we hear a lot and say, well, you know, I have a web secure gateway. Why do I need this? Or you know, I'm using, you know, my firewalls to watch, you know, IP traffic. Those are all great, but DNS is actually a very interesting and new choke point. So we're going to talk about these things a little bit in the conversation. Any questions so far? Yes, sir.
Are DNS servers engaged when you explicitly specify an IP address?
DNS servers can be engaged. DNS servers can have IP address blacklists in them, so they're going to resolve to an IP address. So you could actually put an IP address in a DNS server and say, don't go there. But generally, if, let's say, a piece of software has a hard-coded IP address in it, then DNS server is not engaged. And Ryan, keep me honest here. Is that fair? Yes, sir.
So can you clarify, maybe I missed it? So you're talking about two different types of DNS DDoS. You're talking about DNS reflection attacks whereby somebody is spoofing the source IP address and maybe sending it out to millions of DNS servers and then getting those millions of DNS servers to now redirect
yes.
to the spoofed IP address.
Yes.
But then you were also talking about DDoS attacks on your DNS.
Yes.
Okay,
Yes.
So two different things you're talking about.
So when it comes to DNS, there's a whole range of different attack varieties. Some of them are attacks on you, where you're the target. Sometimes you're the accomplice. In the case of the reflection attack, your DNS server may not be the attack or the target. It may be the accomplice in attacking someone else. In either case, you want to be able to detect that and prevent it. University contacted us and said that their DNS servers were pegging very, very high query rates for the whole weekend. And they weren't really exactly sure what was going on. They were looking at the query logs and all of that. And what they realized was that they weren't being attacked. They were being used in an attack against someone else. They were part of a reflection attack. So we helped them through that. And that's something that you have to also avoid. Okay, so good clarifying question. And it gets even more complicated, because as we see in an example like what happened about a year ago in 2013 August, DNS servers can also redirect to malicious destinations where the domain registrar is compromised. So this is the Syrian electronic army attack example where some smart guys, some smart bad guys, they actually through social engineering got the passwords and got into the domain registrar in Melbourne, Australia, which happens to house the name server of New York Times and Twitter, the EMEA servers of New York Times and Twitter. And that is the authoritative IP address for that server. Remember the DNS system that I told you about? That IP address that's sitting in that registrar defines the official address of the New York Times website. Okay? And that's the IP address that goes into all the DNS servers in the world, and that's how people find it, right? So the Syrian electronic army guys, and I don't know if they're related to Syria, by the way, that's what they call themselves, they went in and they hacked into that domain registrar, changed the IP address for New York Times and Twitter to be their server destinations. And so for a period of 4 hours in the case of New York Times, when you were in Europe and you did www.newyorktimes.com, you would get that splash screen. Now imagine if that was Chase Bank and you were going in to do some online banking, and what if the bad guys had made that splash screen look exactly like your Chase login, right? And you actually put in your username and password, right? But they didn't, they were just kind of doing it for show. And the same thing happened for Twitter. Twitter figured it out in 2 hours, the New York Times figured it out in 4 hours. And then it took 24 hours for those bad destinations to work their way out of the cache. Remember I told you these things get cached? So there were still people going to these destinations for 24 hours because it has to work its way out of the system. So that's one example where the DNS server itself isn't involved, but the DNS system enables these types of bad behavior. And a whole bunch of different vulnerabilities like cache poisoning and things like that that can just send you to the wrong place because they define where you go, right? So that was one example. So that's called, we call that, what do we call that? We call that domain hijacking. So that's we named that one. It's a domain hijacking attack and has nothing to do with your DNS servers. It's the root authority. All right, here's the one we talked about and you mentioned about the reflection attack. Now, it gets more interesting because this is distributed reflection, DDoS. It's distributed, it's amplified, okay, and it's, excuse me, it's a reflection and amplified. I'm getting off of screen here. So let me tell you, here's the bad guy. He's sending a spoofed query, which means he sends a query that has the address of the target victim in it. And the open resolvers that we talked about, these open recursive servers, they're going to respond. So they respond. Now, the way that they shape this query is in a way that it actually creates an asymmetric response. So they ask for some additional information like what's your version of bind, and maybe they turn on DNSSEC and all of that kind of stuff. So my 10 kilobyte query creates a 100 kilobyte or 1,000 or 1 megabyte response. Now, if I can send these spoofed queries to enough open recursive servers, how many of them did we say there were in the world? 33 million, right? 33 million of these. If I can send these and all of them answer back with the large response payload to the attack, that's how you DDoS your attack, your victim, using open servers out there. Now, you can, if you use, there's a simple fix for this, and everyone should know about it, but if you implement a patch called source address validation, that goes away. Source address validation says, well, you know, what's your IP address? I'm going to authenticate who you are who you say you are so that I'm not taking a query from one place and then sending it to another. It's a simple fix, but a lot of people still have not implemented it. There's still a lot of open resolvers out there. Does this make sense? Here's another one. This is called DNS DDoS for hire. You can go find these botnet websites now. It's hard to see from where you guys are probably sitting, but it's $800, and you can basically pay with your credit card and get access to these websites that will do DNS amplification, spoofed UDP attacks, HTTP attacks. So these are DDoS servers for hire. And this is how bad the situation has gotten. Now you can go out there and hire this stuff, and if you're really mad at somebody, or, you know, who knows, United Airlines didn't treat you nicely, you know, maybe this side is a bad guy, I'm going to go out there and hit their, of course, United Airlines, their registration system. There you go. Maybe you hire one to attack the other. Gaming networks are seeing a lot of attacks like this, you know, with young, you know, teenagers getting angry that they lost in whatever, Minecraft, and they attack. But this stuff is available, and we actually have an example of a student in a university in Texas that DDoSed the exam servers because he wasn't ready for his final exam. So during exam week, that server goes down 3 times, and they're wondering what happened. They did eventually find him and probably give him a failed grade, but he probably got an A in computer science. And speaking of DNS attacks, here are the varieties. I mean, it goes on and on. Amplification, we talked about, protocol anomalies, hijacking, reconnaissance, fragmentation. There's a whole bunch of exploits that are protocol anomalies and exploits very much designed as shaped queries. They call them sometimes a ping of death. It's like the query that's malformed that'll actually make the DNS server choke and all of this kind of stuff. I mean, it's pretty amazing the number of different ways you can, you know, bring that down. So you got to be able to protect against all these. So a lot of bad news, right? But help is on the way. The cavalry is here. There's a lot of technologies and configurations that are available commercially. You don't need to go to a professional vendor, and you can fix a lot of these pretty simply, and I'll talk through some of these best practices. The first one is, actually I'm going to talk about DNSSEC, collaboration, dedicated appliances, monitoring, RPZ, which stands for Response Policy Zone, and then advanced protection. First thing is get the teams talking. A lot of the problems that we see are networking teams and security teams not really being on the same page regarding DNS. Who owns it? Who's responsible for securing it? Who's watching the logs? Who's really carrying and feeding from a security perspective? What procedures and runbooks do you have if you have an attack? Most people don't actually think through that, right? And when we get the calls, by the way, there are attacks that are happening. By the nature of DNS, DDoS attacks, they tend to last for a long time. You know, the server's getting hit for a couple days or a couple weeks, and you know, they can't figure a way around it, and they can't shut it off because they'd be shutting off good queries. So, you know, do we have tools? Do we have runbooks? Do we have a procedure on being able to detect and then mitigate? A lot of people don't. Would you know if an attack was happening? How would you know? And what would you do about it? So get together with if you're a security person, get together and have lunch with your networking team. If you're a networking person, do the opposite. But talk about DNS and learn about it and dig into it and ask the questions. Are we doing anything? What tools do we have in place? Run some scenarios. Test, you know, your DNS servers. That's the first thing. Second thing, you know, off-the-shelf servers for critical DNS functions, probably not a good idea. If you're running, you know, Microsoft DNS, it comes with the operating system, it comes with the domain controller. Wonderful, okay, great. But if it's a critical function, it probably shouldn't be running on Microsoft, because most of the Microsoft operating system that are running on or that are running on general purpose servers, I should say, they all run multiple ports, right? They're set up for running web applications. They're set up for having ports for email, for FTP. So there's a whole bunch of logical and physical ports on the box that are open and potentially vulnerable, right? I don't want a general purpose operating system. I want a DNS operating system, right? And then what about all the user and administrator level type of privileges that people have in a Microsoft type of operating system, where they can make changes to zone information, for example, in DNS, and have those be unlogged and untracked. So if someone does do something from the inside, you won't know it. You can make unlogged changes in Microsoft to DNS, right? And so that's a problem. And then the other thing is, if it's a mission critical server, you know, if you have to do Patch Tuesday and patch the operating system, you have to reboot the app, reboot the operating system, or reboot the box, right? And you know, a lot of our customers can't deal with that type of, you know, power cycling or rebooting of the server. Hardened appliance approach is the right way to go. Purpose-built servers, generally appliances or servers that are dedicated, they usually just have one port that's open, that's port 53, that's just for DNS traffic. They have tight authority around user level, no OS level kind of privileges. They usually they only have administrative type accounts, and where changes are all logged, so you know if someone's making changes. Generally, if there's box-to-box type of communications, these are usually secure and encrypted communications. And then lastly, you generally, for most vendors out there, you generally can plug these in together and they become highly available pairs. So you don't have to run clustering software and all that kind of stuff. So that's helpful. And that enables, you know, two-factor authentication for the box and yada, yada, yada. There's a whole bunch of things that a hardened appliance will do to protect that server. As we said, that was step one. The second thing is, on any services that you're running on DNS, do some monitoring and alert on things like aggregate query rate. And I know this is hard to see, but it's very simple with most DNS servers to be able to look at your queries per second and put some kind of a alarm on there that says, hey, look, you know, my typical run rate queries per second on a given day at the highest level is 100,000 queries per second. That's pretty high, actually. If it gets to 200,000, 300,000, I want an alert. That tells me that there's potentially something happening that shouldn't be happening. So other types of monitoring could be if, you know, X number of queries are going to the same place. If 80% of my queries are going to the same domain, maybe I got a problem, right? So you can do that in most DNS servers. DNSSEC, This is a Kaminsky vulnerability that was a protocol level vulnerability that was discovered in 2008 by a gentleman named Kaminsky. He's a white hat. So he provided the information to the DNS Sec, standards making bodies well in advance of publicizing it. So there's a patch or there's a workaround. You can't patch a protocol vulnerability. It is a shortcoming of the vulnerability. So DNS Sec, which stands for DNS Security Extensions, was created. And this allows, this prevents the notion of cache poisoning, which is DNS servers are very trusting with one another. And this allows them to share an encrypted key to make sure that they are who they say they are. So now I know that I'm responding to you because I have a key and we validate each other. It's kind of like doing business on a website that has the VeriSign logo on it. That way you know that your information is encrypted and they've been checked out. DNSSEC is something that you can turn on in any bind type DNS server and have it be more secure. This prevents cache poisoning. Advanced DNS protection. This is actually very interesting. Now we're seeing servers out there that are beginning to now look at the query load that's coming in, pre-processing the query at line speed. So before I respond to it, I'm going to look at it and I'm going to see if I can compare it to a set of rules to see that it could be possibly malicious traffic, and then I can just ignore it. It's kind of like we call it one of the guys calls it the blueberry sorter. As the blueberries are going across the conveyor belt, I see some bad ones and I just pop those out. Those are the malicious queries. I can continue to serve up good queries while the amplification and the reflection and those kinds of attacks that I've detected are turned off. And generally these come with kind of a threat intelligence feed into the server that gives you the signatures of these types of DNS attacks. And now I can detect them as they come. So if we detect a new type of attack, then the DNS server is savvy to that type of pattern. Now it's comparing those queries against that pattern and can protect you real time. And generally, reports are created. So that's another way to protect. Response policy zone, again, standard with bind and with these purpose-built servers. Many of them create that have the ability to be able to do RPZ. And RPZ is just basically a very customizable blacklist, which says, if I get a query to a destination, what should we do? What would be the policy? So, for example, if there is a domain, if there's a domain in Moldova, that could be a query that I don't resolve, whereas a domain in the United States or in Europe I will resolve. RPZ is very interesting because it allows you to also bring in all sorts of interesting feeds in to potentially add to the blacklist. So I think FireEye is here. I saw them. FireEye can detect malicious activity in an executable. And if it picks up a domain address or a domain in that executable, it can pass it and you can populate your RPZ with that. So now all of the FireEye detection events can become blacklisted in your DNS server. There's some new feeds that are being created. By the way, Spamhaus has a feed for RPZ as well. There's some new feeds that are being created that are really great. They're called NGDs, newly generated domains. So it's a whole feed of domains that have only been created in the last hour or in the last 10 minutes or in the last 24 hours. It depends on what you want. And it basically says, look, if a new domain was created in the last 24 hours, it probably isn't google.com. That's been around for a while. Don't respond to it. So there's all sorts of interesting ways that you can kind of do these aggregate blocking using the response policy zone inside of your DNS server. Okay? Make sense with me? I'm not going to walk through this. This actually shows a case where someone contracts malware from outside of their network. They go to Starbucks, their laptop picks up a piece of malware. It comes into the corporate network, and now that malware is going to try to call home. Well, if your DNS server knows that bad known destination, it can detect that query that the malware is making to call home, and it can block it and then log it. So this is one way where DNS can help. Yes, sir?
Does it send any information back to the laptop to resolve a problem with the laptop now?
Generally, you can get a type of response which says you just attempted, it'll say we can't send you to that location, you just attempted to access a destination that we feel is suspect, please contact your system administrator. If that DNS server, by the way, most of these DNS servers, they also serve up DHCP, the domain host configuration protocol, right? DHCP is what authenticates most of these mobile devices or connected devices. So then you also have the IP address of the endpoint too, right? So you'll know who actually made the attempt, or the IP address and the MAC address and things like that of the endpoint that tried to make the malicious query. So really good in not only blocking, but also being able to identify the endpoints. Okay? RPZ. So this is where DNS suddenly becomes an asset, right? Because I've got a really good choke point. Everything's got to go through here. Now I can decide whether I want to do green light, red light. And I highly encourage you to educate yourselves around RPZ. So what's the call to action? Well, you guys are the Jedis, right? You guys got to get out there and stop all these bad guys. So don't underestimate the vulnerabilities around DNS, around data exfiltration, around the ability for the bad guys to bring down the systems or use malware to exfiltrate data through DNS. Raise the awareness of DNS in your organization. Work with your counterparts. There's a lot of resources. I only named about 5 or 10 things. We have best practices guides at our table. There's a poster that shows you in great detail what all the things you could do. And then seek help. If you want, you can talk to the experts. That's us. And I'm going to spare you the commercial, but we're in the DNS business, and we'll skip over that and go to Q&A. Yes, sir.
I've been reading this article in Wired, and the article was on how to improve the internet, or all the attacks and stuff. And one suggestion was to actually create a new protocol, updated protocol, and just put stuff like for example, the electrical grid on it. And you'd actually have kind of two internets, but one would be the newer protocol, more secure. How do you feel about something like that?
Yeah. I think there's a lot of good thinking happening around that. And in fact, with this whole Internet of Things, there's the movement from IPv4 to IPv6. It's hard. I think that my opinion, and I'm far from being an absolute expert, is that I think the Internet protocol has won the day in terms of device to device or application to application communication. So maybe not in my lifetime. There's a future where there might be a protocol that might get introduced to supplant IP or TCP/IP. I don't see it happening in the near future. I think the way that IPv6 and the size of that address space is enabling us to have unlimited, unfettered growth in terms of devices and endpoints. I think that's going to be the order of the day. We just have to figure out how to secure the rest of the network around it, in my opinion. Any DNS people in the room? Anybody have a responsibility for the domain name system or work closely with it? Does this ring true or ring accurate? Yes, sir. It does. Yeah. Do you work with it yourself, or?
Yeah, I'm with the enterprise architect, so I'm not directly responsible for managing it, but I have to do it.
Okay. Okay. Well, hopefully this was helpful. Yes, sir.
I'd like to share an experience that we have. We have BYOD. We have some state computers that connected to a non-state network. And then when they connected to the state network, we started to notice that they were trying to connect each other. So we brought the laptops into the lab, investigated them, could not figure out what was wrong, cleaned them up, refreshed them. Then the laptops went out, and then the same thing happened. So what was happening was the access point system that they were using was infected. It was poisoning the DNS stash. What they were doing was they would connect, close the lid, put it to sleep, go back to the corporate network, connect, and then it was still poisoning.
That's how they would do it,
The
yeah.
lesson learned was that you're looking at setting a policy that if you connect to a non-state network, that you need to reboot the device before
That's interesting.
whether they connect at home or whatever, you just never know what's in there.
Right.
fortunately, we were able to block it.
Nice. Geo-blocking does help. That's really good. We had a similar instance where one of our customers, it was a hospital, couldn't figure out why an ultrasound machine kept trying to call China. And so they contacted us, and we took a look. And a lot of the medical equipment have an FDA-approved version of Windows XP on it. And once you get a version of an operating system kind of through the FDA approval process, you don't change it very often. So this thing had an older, fairly unpatched, out-of-date, unpatched version of an XP on it, and they're on the network, so it picked up malware. And malware, generally, the initial payload is usually very small, as you know, right? So it's just really small and unobtrusive, and all it's going to try to do is call home and pick up the rest of the instructions. So that's what they were picking up. And so they decided that they were going to put a pretty significant DNS layer type of geo-blocking in, so that if an MRI machine or something was trying to call China, they would know. But similar experience. Thank you for sharing that. That's very cool. Any other comments or questions? Just show of hands, was the information that I shared with you kind of new and novel, or did you already know it? If you gained something interesting out of this, raise your hand. That's great. That's great feedback. Thank you very much. Well, I know that I'm pretty much out of time. If there are no other questions, I want to thank you all for your attention. Thanks.
Thank you.